Okay, so get this. Most of the matter in the universe is actually, well, invisible.
Yeah.
It's this thing called dark matter.
Right.
And today we are diving into a paper that suggests, get this, not one, but two ways this mysterious stuff might be made.
Yeah, it's really intriguing. You see, we're so used to hearing about WIMPs.
WIMPs.
Yeah, weakly interacting massive particles. Like, that's been the leading candidate for dark matter for so long.
Right.
But this paper, it explores something completely different. It's called the freeze-in mechanism.
Okay, freeze in. I mean, it sounds kind of cozy, like a winter getaway for, like, particles. What's the deal?
So picture this, the very early universe.
Okay.
Like a fraction of a second after the Big Bang. Everything is unbelievably hot and dense. Imagine a cosmic soup, right? Just simmering away.
Okay, I'm with you. Yeah.
As the soup cools down, most particles, they freeze out. They form the matter that we see all around us today, the stuff we're familiar with.
Right.
But, and here's the catch, some particles, they interact so weakly that they never fully join the party. They never completely freeze out.
Oh.
They just linger, like a subtle aftertaste.
Oh.
And that, in a nutshell, is freeze in.
Okay.
And those lingering particles, they could be our dark matter.
So while everyone else is at the cosmic buffet, these particles are, like, hanging back, slowly sipping their cosmic cocktails.
You got it. And what's really cool about this paper is that it brings in two key players to this cosmic cocktail hour.
Okay.
The first one is our dark matter candidate.
Okay.
It's a particle called Kirch. It's this, well, we call it a FIMP.
A FIMP.
A feebly interacting massive particle. Basically, it's even more standoffish than those WIMPs we talked about.
Wow, even more of a loner.
Oh, yeah, it barely interacts with anything, hence the whole feebly interacting thing.
Sounds like my kind of party guest, honestly. No pressure to make small talk or anything.
Okay.
But, okay, if this is so aloof, how does it even factor into, the grand scheme of things?
That's where our second key player comes in. This one's a much heavier, much more sociable particle.
Okay.
It's called Feebly.
Got it.
Think of Feebly as the life of the party, interacting with all sorts of other particles in the early universe.
Right.
But, and there's always a but, Feebly is unstable, it eventually decays, and one of its favorite decay products is our friend.
So Fiddy is like the social butterfly that brings the mysterious loner to the party as a +1.
You got it. And this paper, it explores two main scenarios for how this interaction between Feebly and Shu could have gone down in the early universe. And ultimately, this determines how much dark matter we end up with today.
Okay, two scenarios, two potential origin stories for dark matter. Lay it on me.
All right, so the first scenario, it's called slow and steady wins the race.
Okay.
Or, freeze and dominated. Here, our social butterfly, Feebly, is mingling at the cosmic party for a good long while, right?
Oh.
Interacting with other particles. It slowly decays into over, like, a long period.
So a slow and steady trickle of dark matter creation.
Exactly.
What about scenario 2?
Scenario 2, it's like a cosmic inheritance. We call it the Big Bang legacy, or super WIMP dominated.
Yeah.
In this scenario, Feebly makes an early exit from the party, freezes out quickly.
Right.
But here's the thing, when it goes, it leaves behind this huge inheritance, a massive amount of itself that then decays into...
Hold on. So in one scenario, we have this long, slow drip of dark matter creation, and in the other, it's like a sudden windfall.
Yeah.
That's kind of a big difference, isn't it?
Absolutely. And what determines whether Feebly is a party animal or an early bird all comes down to how strongly it interacts with other particles.
Okay.
Imagine these interactions like stickiness.
Stickiness, okay.
Yeah, so the stickier Feebly is, the longer it hangs around before decaying, leading to that slow and steady freeze-in scenario.
Right.
But if Feebly is less sticky, it makes a quick exit, right?
Right.
Leaving behind a larger inheritance, leading to more dark matter being produced kind of in one go.
So the strength of these interactions is kind of like a cosmic dimmer switch,
Yep.
controlling the brightness of the dark matter signal.
That's a great way to put it. And you know what? The paper actually gets even more specific, digging into the precise parameters that dictate these interactions.
Okay.
They use, mathematical terms.
Of course.
Like LSD and OB.
Right.
But essentially, these are like dials that researchers can adjust to control just how sticky FDD is in their models.
Okay, so by tweaking these dials, researchers can essentially simulate different cosmic scenarios and see how they affect the amount of dark matter that's produced.
Precisely. And they've even created like graphs and figures showing how changing these parameters changes the amount of dark matter we end up with.
Oh, wow.
It's like they're mapping out the cosmic recipe for dark matter.
This is where it gets really interesting. If these scenarios lead to such different dark matter production timelines, wouldn't that leave a noticeable mark on the universe?
That's a great point.
Couldn't we look for these marks to see which scenario is more likely?
That is a fantastic question, and it's definitely something researchers are actively investigating.
Yeah.
They're running simulations, right, to see if a slow and steady freeze-in of dark matter would look different from a rapid, like, inheritance scenario on a cosmic scale.
Okay.
Imagine if we could create a dark matter map of the universe.
Right.
The patterns on that map, whether the dark matter is, smoothly distributed or clumped together, it could tell us a lot about how it was produced.
So we're talking about potentially using observations to test these theoretical models.
Exactly.
But wouldn't detecting something as elusive as dark matter be incredibly difficult? Even with a map, I mean.
You're not wrong.
Yeah.
It's a huge challenge. Dark matter doesn't emit light.
Right.
It doesn't interact strongly with ordinary matter, which makes it incredibly hard to detect. But, astrophysicists, we've got a few clever tricks up our sleeves.
Okay, I'm all ears. What kind of tricks are we talking about?
Well, one approach is to look for the subtle gravitational effects of dark matter. Even though we can't see it directly, dark matter's gravity, it affects the way galaxies rotate
Okay.
and how light bends around massive objects.
Right.
By studying these gravitational anomalies, astronomers can kind of infer the presence and distribution of dark matter.
So it's like, someone is sitting on the other end of a seesaw, even if you can't see them, just by how it's moving.
Exactly. And there are other experiments looking for, the really, really faint signals produced when dark matter particles very, very rarely interact with regular matter.
Right.
If we're lucky and has the right properties, we might just catch it bumping into something in one of these detectors.
It sounds like we're talking about some seriously sensitive equipment and like some mind-blowingly rare events here.
Oh, absolutely. But, that's the thing about dark matter. It's the ultimate hide-and-seek champion. And finding it, well, it's going to require incredible ingenuity and a good dose of cosmic luck.
Speaking of ingenuity, this paper dives into a lot of, complex physics to explain these scenarios. There's talk of Boltzmann equations and a whole bunch of other stuff that's probably going to make my brain melt if we try to cover it all.
Yeah, you're not wrong.
Yeah.
The math can get pretty intense, but at its core, the paper uses these equations to model how the amount of both phi d and sinh changes over time in the early universe.
Okay.
Think of it like a cosmic accounting system. These equations track how particles are created, destroyed, and interact as the universe expands and cools.
So kind of like a census for the early universe, tracking the comings and goings of all those particles.
Exactly. And by solving these equations for the different scenarios outlined in the paper, the slow and steady versus the big inheritance, researchers can see which one produces the amount of dark matter we observe in the universe today. It's like fitting puzzle pieces together to see which one completes the picture.
It sounds like we've got this whole cosmic mystery unfolding. We've got the aloof dark matter particle and its sociable counterpart, phi d. We've got two potential scenarios for how they interact, and we're using like complex equations and cutting-edge experiments to try and figure out which scenario, reflects reality.
Right.
But there's one more thing mentioned in the paper, BBN.
Yes.
What is that all about? What role does it play in this whole cosmic drama?
BBN. It stands for Big Bang nucleosynthesis. Basically, the period in the early universe when the first light elements were formed, like hydrogen and helium.
So like a cosmic cooking show. But instead of a delicious cake, we're making like the basic ingredients for stars and galaxies.
Yeah, that's a tasty way to put it. But here's the thing. If fire sticks around for too long, its decay products, they can mess up this whole delicate cooking process.
Yep.
It's like leaving the oven door open at a crucial moment. You might not get the results you were hoping for.
Okay, so if EP can't just party forever, it's got to make a graceful exit before it spoils the cosmic soup, so to speak. But how do we know if it exited on time? Are there like any telltale signs we can look for?
Well, that's where those incredibly precise measurements of the light elements in the universe come in.
Okay.
They give us a really good idea of how BBN played out. And by comparing those measurements to the predictions of our different dark matter scenarios, well, we can get a sense of whether Feedy was a party animal or an early bird.
So it's like using a cosmic clock to make sure Feedy didn't overstay its welcome.
Exactly. We're essentially using the abundance of those light elements as a cosmic timestamp.
This is blowing my mind. We've gone from like invisible particles to cosmic cocktails to a recipe for the early universe, all in an attempt to track down dark matter. But before we get too lost in the cosmos, can you remind me what makes this particular paper so important? Why should we care about these specific scenarios?
Sure. You see, most models of dark matter production, they rely on a single process happening at a specific time in the early universe.
Okay.
What makes this research so intriguing is it presents us with options. It's like, it says, hey, maybe dark matter wasn't made in just one way. Maybe there are multiple pathways, each with its own unique fingerprint.
So it's not just a new recipe, it's a whole new cookbook for dark matter.
Right.
And each recipe leads to a slightly different outcome.
Precisely. And that's why those observational tests we were talking about, they're so crucial. If we can find evidence for those unique fingerprints, those subtle differences in the distribution of dark matter, or the properties of those elusive particles, it would not only revolutionize our understanding of dark matter itself, but give us a glimpse into the very earliest moments of the universe's existence.
Wow. Okay, now I understand why this research has got everyone in astrophysics so fired up. It's like finding a hidden treasure map that could lead to not one, but multiple cosmic secrets.
Exactly. And who knows what other mysteries might unravel as we continue to follow these clues, right?
Well, one thing's for sure, we'll be keeping a close eye on this research and all the exciting developments to come. In the meantime, for those listening, if you want to impress your friends with your newfound knowledge of dark matter, just remember those cosmic cocktails.
It's not just accurate, delicious science.